Good afternoon. Welcome to an Ethics Roundtable on engineers who make selfish machines. I am Tracy Gonzalez-Padron, the director of the Daniels Fund Ethics Initiative, a collegiate program at UCCS College of Business, and a professor of marketing, international business, and strategy. Roundtables provide us an opportunity to hear about how others teach ethics and implement principle-based ethics in their work or area of expertise. It is my pleasure to introduce Philip Brown. Philip is an assistant professor in the Department of Computer Science, and he received his PhD in electrical and computer engineering in 2018 from UC Santa Barbara, and is interested in the impact of human social behavior on the performance of large-scale infrastructure and software systems, and studies this by combining concepts from game theory and feedback control of distributed systems. Philip is also serving as a Daniels Fund Ethics Initiative Ethics Fellow for the 2020-2021 academic year. So let's hear from Philip.
Hi, thanks a lot for the introduction, Tracy. Thanks everybody for being here. I'm excited to talk about some of these things I've been thinking about lately. So for a brief kind of verbal overview of where we're going, the goal of this talk is to introduce some things I've been thinking about that focus on how I think we need to update how we teach ethics to engineers. I think the old model of ethics engineering training is important, but has some gaps that have opened up in the 21st century that perhaps need to be addressed. So I want to talk a little bit about what that looks like, and I'll start by giving you my picture of what I will call the traditional picture of ethics engineering or engineering ethics training. So when I was in my undergraduate program in electrical engineering, I was taught about engineering ethics from the standpoint of a bunch of different case studies. And these are all case studies of places where engineering ethics failed. So something went catastrophically wrong in the design process, which led to people, in most of these cases, losing their lives. And in some cases, many people losing their lives. So I'm going to focus on one, and I'll just kind of run you through it. And then I'll tell you what I think the core message is of the traditional engineering ethics education. So I'm going to focus on the Hyatt Regency walkway collapse example. So this is it was an event that happened in 1981 in Kansas City, and it was during a dance party of some kind in the lobby of this Hyatt Regency hotel. And what happened was there were these two long walkways that were suspended over the dance floor. And at some point during the dance, there were, a few dozen people up on the walkways. And apparently the weight of those people was enough to cause the walkways to collapse to the ground. And so it was this huge thing in national news, and there was this huge inquiry into why this thing happened. And the basic conclusion was it was this systemic neglect of proper design review. So at several stages along the design process, people didn't do the things they were supposed to do, didn't subject the designs to the right questions, and this thing failed. And so you can see the picture on the right, those two red squares that I put up show where the walkways had connected to the hallways on the second and fourth floors, and that's where they detached. So here's the basic story of what happened. The engineer went to the fabricator and gave them designs that said, build this thing. And the fabricator said, that thing you suggested, it's probably going to be pretty hard to build. Like those long tie rods are going to be hard to source. Would it be okay if we did this? So they suggested a modification. And the story goes that over the phone, the engineer said, yeah, sure, go for it. Without subjecting it to an additional layer of design review. And so it turns out that in retrospect, it's clear to see that, at least if you're a structural engineer, it's clear to see that this design on the right only supports half of the load of the design on the left. So the fabricator's modification weakened the design by a factor of 2. And it turns out that the engineer wasn't doing their job either, because the original design was only 60% of as strong as it was supposed to be, according to Kansas City code. And so the engineer made an initial mistake. The fabricator did something which made that worse, and then the engineer didn't check to make sure that was not, that wasn't causing problems. So the story of this ends up being that the engineered system was this monolith that was supposed to be totally independent of the social system. So regardless of how the social system that this walkway was serving, regardless of how the social system used it, the engineered system was not supposed to cause damage or cause harm to this social system. And so I interpret this, or the way I kind of see this, and this works for all of these different examples, is that the ethics message to engineering students is engineer stuff that doesn't break. Or if you're super sophisticated, maybe you say engineer stuff that if it breaks, it doesn't hurt people, like it fails in a safe way. And the hidden implication here is that engineering is about designing these monolithic systems that are independent of the social systems that they serve, and that these monolithic engineered systems ought to be able to be analyzed kind of in isolation, and that if you just design that isolated engineered system properly, that's good enough. Like, you've done your job as an engineer, as an ethical engineer. You've kind of fulfilled your obligation to society if you just can guarantee that the technical aspects of your engineered system are correct. The problem is that today, and by the way, I think this is a good message. I think this is a critically important message, and we shouldn't walk away from telling this message, right? We have to get technical designs correct. I think that's true. The problem is that engineering is changing now in the 21st century. And now the connection between the engineered system and the social system tends to look more like this. We tend to end up with feedback loops between our engineered system and our social system that make it very, very difficult to analyze the engineered system in isolation from the social system. So let me give you a couple examples of the kinds of places I think this arises. And then what I'll do is I'll walk you through some thought experiments about why the connections, the two-way connections between engineered systems and social systems change the question that we have to ask as engineers. So I think this began in the late 2000s, or maybe even the 90s, with e-commerce applications. So this was one of the first times that we saw people who had merely technical training, right, had no training in social science, constructing things that were then used in a social way. And so, I put up eBay, but you can think of all kinds of early kind of internet type systems that were created by software people, but used socially. I think maybe MySpace was an early example of a social network that did something like this. And there's a case to be made that in eBay, there's not a lot of harm that can come from the social embeddedness of the engineering. But fast forward 15 years, and you get systems like Lyft and Uber, which the operators of Lyft and Uber continue to insist that they are merely software. Right? All they're doing is creating a software product, and people can use it however they want. But now they're creating a software product whose purpose is to connect human beings together. So Lyft and Uber they have these algorithms that suggest who rides with whom, and those algorithms put strangers in vehicles together. Right? They put strangers in potentially dangerous situations together. So there are deep social implications to what those software systems do. So another area where this starts to look potentially even more dangerous is in smart infrastructure systems. So I had this infographic of a smart grid system. For those of you who aren't familiar with the term smart grid, it's this idea that we should be transitioning our electricity distribution grid, so the transformers and power plants and power lines, into a system that's more carefully integrated with society. So this leads to things like smart pricing of electricity, where you change the price of electricity as a function of how much it costs to generate at that time of day, so that you can kind of shape the way people decide when to plug in their electric cars or something like that. But we end up with in this smart infrastructure, and we see this in smart grid and smart transportation and this whole litany of other smart X applications. We see this increasing intertwinement between the technology and the people that are served by the technology. And one of the things that I focus on in my research is I like to ask, how does feedback change stuff? So how does it change the question when you link two things and cause them to depend on each other that didn't used to depend on each other? And the answer is things get complicated. We'll talk a little bit about that in a minute. So there's a variety of other examples. I'd like to put up a couple other pictures, but I hope you get the picture that there's an increasing participation of engineered stuff in social settings nowadays that there didn't used to be. And that increasing participation of engineered stuff in social settings can cause some unexpected things to happen. So a couple questions that I'm interested in are, first, why, or interested in conveying to people when I talk about this stuff is, first, why does the feedback loop matter? And then second, what are the ethical implications of this for engineers and for training? And then how do we teach these new issues? So today, I'm not going to be able to get into the guts too much about the first question. So why does the feedback loop matter? Is a very complicated subject. But one of the things that I can say just kind of verbally about why the feedback loop matters is that once you put these two things in feedback with each other, it becomes very difficult to assign blame when something goes wrong. So if you think about some of those examples I had up on the slide earlier, one of them was the Bhopal chemical plant disaster. So if you haven't heard of the Bhopal disaster, this was something that happened some number of decades ago. I don't know the exact year. Happened at a chemical plant in India where something went wrong at the chemical plant, and poison gas was just released onto the neighborhoods around. And so the company that owned the chemical plant, they can blame whoever they want, but they certainly can't blame the victims. Like, it's very, very clear that the victims of the disaster were not in some way a cause of the disaster. And that's because there was no feedback between the chemical plant and the victims of the disaster. In something like a huge pileup on a freeway, it becomes much more difficult where now there's some feedback between, so say there's a Tesla with a self-driving algorithm controlling it and it crashes into something else. It becomes more difficult to disentangle the blame in a situation like that. So one of the challenges with feedback is it kind of muddies the water and it makes it difficult to assign blame and thus difficult to assign responsibility. But let's think through some thought experiments now about why embedding engineered stuff in social systems can make things challenging and can make these questions difficult. And the first thing I'm going to start with is a thought experiment about robots and escalators. So as I was putting this slide together, I realized that I barely remember what it's like to ride on an escalator. Like, I don't think I've been on an escalator in over a year because of the pandemic. But if you recall, it's this thing where you got on it and it took you up the stairs and you crammed together with a bunch of other people. And that feels a little bit alien to my current experience right now. But if you think about how humans use escalators, at least this is common in the West, we all have this kind of unwritten rule that when you get on an escalator, you stand on the right if you want to stand, so that you leave a walking lane open for people on the left. And this is kind of huge, the human intuition about how to use escalators. And it feels like the considerate thing, right? The goal is to make sure that if somebody wants to get where they're going fast, they have the ability to do so by walking. And the human intuition here is you don't want to be that guy, right? You don't want to be this jerk of an individual who's standing in the left lane and blocking everybody behind them. And the feeling we have in our minds is that if somebody decides to do that, they're valuing their laziness, right? Their desire not to walk over the time of the people behind them. We're a very time-focused society, so this feels like a violation of other people's independence or something. In other words, this feels unethical, right? To a human who is self-aware, it may feel unethical to stand in the walking lane on an escalator. Right? It feels rude. So now let's imagine in some future we have robots walking around this shopping mall or whatever kind of place this is. Maybe it's a subway station or a shopping mall or something. Imagine we have robots walking around, and maybe they're cleaning robots, or maybe they're security robots or something. But they're these now autonomous entities that have been designed by engineers and programmed by engineers who occasionally need to use the escalators. And so the question that we can ask in this thought experiment is, what should the robot do on an escalator, right? What should the robot's designed escalator policy be? And we can list some of the possible policies, and there's basically three, right? Policy one is this low impact policy where you make the robot stand in the standing lane. Policy two is maybe you want to prioritize the robot's ability to complete its next task quickly and get where it's going quickly. So maybe you program it with this selfish policy that we see in the middle. And then just for completeness, we'll put the one last policy that you could do. You could program it to stand in the walking lane, right? The kind of the jerk policy, what feels like the if it were a human, it would be an unethical policy. And it feels like, just looking at this, applying our human intuition to this, and maybe anthropomorphizing the robot a little bit, it feels like we should do anything but the one on the right? Clearly, that's not what we should do, because that would make the robot a jerk. But it turns out, if you went and asked a systems engineer, like a human systems engineer, such as Professor Leslie Strotterman at Mississippi State, who I owe this example to, you would actually learn that this is the way to maximize the capacity of the escalator. It turns out that if escalators are crowded, so in other words, if there's a big crowd of people down at the bottom of the escalator waiting to get on, the way to clear that crowd fastest is actually to have everybody stand on the escalator. And so briefly, the reason for this, this feels super unintuitive, and I agree I read this article online, and I thought, this is impossible. There's no way this is the case. Sent it off to my grad students and said, figure this out. And the consensus was, she's probably right. It's probably correct that standing is the best way to do this. The reason is just that if you're walking, you have to put some space between you and the person in front of you. And if you don't, then you're liable to trip on them. And even if you're not tripping, you're making them feel super uncomfortable if you're walking really, really close behind them. So humans tend to space themselves out by like a stride length or more while they're walking. And that extra space that they put it decreases the capacity of the escalator so much that it's actually better if everybody just packs in and stands. So anyway, here's the systems perspective tells us that if we care about maximizing the efficiency of the escalator in terms of human throughput, we actually should do this. So I'm going to call this on the right, I'm going to call this the altruistic policy. So let's compare now the selfish policy for the robot and the altruistic policy from the standpoint of kind of who is benefiting and who is being harmed. So if we start with the selfish policy, the selfish policy benefits the robot, certainly, because the robot gets where it's going faster. And it benefits a couple people behind the robot because they don't have to stand there waiting. They get to walk if they want to. But it turns out that because it doesn't maximize throughput, it actually harms everybody else. So all these people waiting to use the escalator are worse off and will get to the top of the escalators more slowly because the robot decided to walk. On the other hand, the altruistic policy is exactly the opposite. So it benefits everybody waiting to use the escalator, but it harms these couple people that are right behind the robot. And of course, it means the robot has to slow down itself. And so now let's start to ask anyway, an ethics question. So if the engineer is ethical, what should she do? How should she program this robot to behave? And I'm not going to give you a packaged answer, but what I want to illustrate is that the fact that we have now a piece of technology operating in society makes this question more difficult than it seems like it should have been. So in other words, if we do the altruistic policy, then this is good for the system. Like, this is the utilitarian optimal thing to do. And in fact, it's good for most of the individuals, right? Most of the individuals benefit from this policy. But it requires you to make the robot look like it is being unethical. So the robot appears to be this this kind of lazy, it just stands there blocking everybody machine, even though it's really helping. So there's a very clear possibility of a misinterpretation by the people behind it about what's going on. On the other hand, the selfish policy is bad for the system. It's unambiguously hurts more people than it helps, and yet it makes it so that the robot appears to be playing by the rules of everybody else. And so I'm gonna pause here and see if anybody has any interesting questions or feedback about this. But this is kind of my first example of strange ethical conundrums that can arise when you start thinking about embedding technological autonomy into society. So does anybody have any questions or feedback before I move on to the next thought experiment?
I just think, as our own city considers smart COS and the Internet of Things, how important it is to make sure that systems aren't just optimizing themselves without the social component.
Absolutely.
And that's why I was so interested in this lecture today, is making sure that there's some understanding and some voice, even locally, as they roll out smart parking meters and smart not flashlights, like traffic lights.
Street lights.
Yeah, street lights.
Oh, yeah, right.
And hoping that there is a feedback loop in the design process where people don't lose a sense of privacy versus public safety and that kind of thing. So I love your example, but I think it is something that beyond engineers citizens are gonna have to start thinking about this too, and holding engineers accountable. So I'm glad.
Right, absolutely. I think one of the big paradigm shifts that I feel is becoming more and more prevalent is that this is stuff that engineers in some ways didn't used to have to think about. Like engineers didn't used to have to think about that what is good for society here. They were just working on their piece. But now partly because of the Silicon Valley kind of move fast and break things culture and things like this, we're seeing more and more people who are trained only in programming and computer science, creating things and programming things that have this social component to them. So yeah, thanks a lot. I would love to chat further about how to do this well. This is something that I think is really important. Bruce, I see you're on video.
Oh, yeah. So, we have like special situations that might be rare but very impactful, like a person who's very ill and has to be carried by a stretcher up one side, and the whole thing with the emergency vehicles and the pulling over. I mean, those are hard to average out and say that. Also, this is a waiting situation, which is maybe pretty rare. So there's kind of an average situation, and then there's the opportunity for the robot to pull over to the right if it's not crowded. So these things become somewhat complicated, don't they?
By all means, yeah. One of the things that I spend a lot of time doing is explaining very simple thought experiments. Sure. And part of the pedagogical message is if the answers are ambiguous in a simple thought experiment, they can only get more complicated and more challenging when we add this complexity. So I think the question of, does there need to be a lane open for emergency personnel? I think that's a really interesting question. Can you compare that to some average world where people wait a minute less or something like that? Like, does that minute less that they have to wait have health benefits that outweigh the time critical nature of getting a stretcher up the escalator? So I agree. These things are the complexity balloons.
Yeah, good.
So
thanks.
This is Charles.
Hi, Charles.
I'm Charles Cummings. Actually, I don't know why my full name didn't show up. I'm a project manager and architect in planning, design, and construction.
Yeah.
And I just want to add an observation. This actually gets embedded in people's work roles as well. Okay. So in my projects, all the engineers work for me, right? They rely on me to make this decision, in which I work with our stakeholders or whatever. trying to think about the public good. So I am in there are people in these processes who are actually enablers of old school sort of thinking about these sort of things, Yeah. And anyway, this is a good example, and makes me think about what I'm doing and how to use it. But anyway,
I guess that's the dream. So very good.
Right.
Yeah.
By the way, your first example of the Kansas City walkways, that accident permeated the first half of my career. So talked about all the time. Yeah.
So I apologize for my quick and dirty and probably wrong approach to it.
Pretty good. Pretty close. Yep.
All right. Very good. All right. So thanks. Let me move on to thought experiment number 2. And so this thought experiment says there's a clear distinction between what selfish and altruistic means, and if you're altruistic, that actually might make you look like, if a robot is altruistic, that might make it look like a jerk. But it's not clear that that's necessarily good or bad, depending on the situation and the context. So traditional ethics message: engineer things that don't break. Our new ethics message needs to include a component that says, understand the interactions between your machines and the people that they serve. And I'll say it again. I've said it before, and I'll close with this as well. But the main thing is we need to understand our systems in integration, not in isolation. So what I'm going to think about a transportation engineering problem now. And so this is connected to, I tell people probably 70% of my PhD work and now some of my ongoing projects. So I want to acknowledge the National Science Foundation's support for this area of research that I've been working on. So, when you choose a route in a transportation network, say you want to go from UCLA to Caltech, one thing you could do is you could pull up Google Maps and say, what's the fastest route? So here, the fastest route looks like it's through LA, but you could also go the longer way around through Glendale, and it would take a couple minutes longer. So a human might do this and say, I'm going to take the fastest route. I'm going to take the one that's 42 minutes and avoid the one that's 47. But now we're entering this time when we might have self-driving cars on the road that get to make their own choice. And so one thing they could do, certainly, is they could query the Google Maps API and say, what's the fastest route, and then take the fastest route. But it turns out that's not necessarily always the best thing to do. And so let's imagine, and what we're going to do is pose a very simple model. And so here in the process, you'll learn a little bit of game theory and see a simple model of the kinds of things I do. But know that this model is mathematically principled, or at least it's based on a mathematically principled model that is absolutely central to the research that I do. So here's our basic approach. Is we're going to say, suppose there's some vehicles on the road, and we live in a world where the engineer can program some of these vehicles to choose their own routes across a city. And so the question is, should this engineer program the self-driving cars to be selfish and take the fastest route? And selfish here, I say this and I realize there's moral connotations to this, but I'm just going to mean delay sensitive when I say selfish. So if I say be selfish, I mean take the fastest route. Or should the engineer program the vehicles to try to do something that reduces kind of system level traffic congestion? And so here's what we're going to do. And this is, I will repeat, a thought experiment. It's not meant to be a highly expressive model. So I'm going to take my map of California and I'm going to reduce it to a 2-route network. So here we're just going to pretend there's 4 cars, and each of those cars has to choose which of those 2 roads it's going to take from the source node to the destination node. And so these roads are different, and here's how they're different. If a car takes the blue road and there's not many other cars on that blue road, then the trip is fast. And the way we'll model that is we'll say for every car that's on that road, the travel time is an extra 15 minutes. So if there's 1 car, then it takes 15 minutes to go across the road. If there's 2 cars, it takes 30 minutes, 3 cars, 45 minutes, and so on. So that's the top road. It's fast if there's not too many cars on it, but it's congestion sensitive. So it will over congest if too many cars use it. So the green road on the bottom it's slow no matter what. So think of this as like a wide highway that goes through some suburb and then comes back to where you want to go. That goes way out of the way, but it's not congestion sensitive. You can just pack a ton of traffic on there and it'll always take an hour, whether there's a lot of cars or a few cars. So let's think about now how assigning traffic to these different roads affects the kind of the total travel time of society. So we're going to measure society's travel time in vehicle hours. So what we'll do is we'll say, suppose I sent 3 cars on the bottom road and 1 car on the top road. Well, each of those 3 cars on the bottom road are taking an hour to get where they're going. The 1 car on the top road is getting where it's going fast, so it's getting there in 15 minutes. And so let me just add up those travel times, and that's the cost of this allocation of cars. So here we've got a total number of vehicle hours on the road of 3.25. So it turns out that if I take one of those cars on the lower road and I move it to the upper road, that improves things slightly. So now there's only 2 cars who are taking an hour, and the upper road has gotten a little bit more congested, but it has gotten congested in such a way that the benefits outweigh the costs. So now the total travel time in this network is 3 hours. So because there's 2 cars that are each taking 30 minutes, so that's an hour of time, and then 2 cars that are each taking an hour, so there's 2 more hours. So if we keep doing this, keep moving cars up from the lower road to the upper road, then that continues to increase the time it takes to use the upper road, and eventually you over congest the upper road, and nothing good is happening, right? So now, if everybody uses the upper road, it's clear that everybody is taking an hour to get where they're going, and that's kind of these possibilities, that's the worst thing that could happen. So, if you look at these 4 possibilities, this option here is clearly the best, and it's the best in a bunch of ways. One, it's the utilitarian optimal. So it's the one that minimizes the total number of vehicle hours on the road. But it's also Pareto optimal. So for you decision science nerds, Pareto, or for you who aren't decision science nerds, Pareto optimal just means that none of these cars in this scenario where we're splitting half and half can switch their decision and become better off without making somebody else worse off. Right. So this is a good scenario in 2 different ways. However, it's not a stable scenario. So if you imagine being one of those cars on the lower road who is taking an hour to get where they're going, you might look at the other road, you might pull up your Google Maps and say, hey, if I'd taken the other road, it would have only taken me 30 minutes. And then the next time you have an opportunity to choose, you might choose the upper road. So there's this strong incentive for individual cars to switch to the upper road. And if they all do this, then we end up with this allocation on the right, which is worse than the allocation on the left. So this discrepancy between what people are individually incentivized to do and the thing that they sort of should do from a system optimal perspective, this discrepancy actually has kind of a catchy name in my discipline. It's called the price of anarchy. So the story of this network is that if you let people follow their own incentives and do whatever they want, in other words, if you let them just go with anarchy, that has a price, right? That leads to outcomes which aren't necessarily optimal in the big picture. So now suppose I'm an engineer and I come along and I say, let me now program maybe even just one of these cars to be altruistic. And let's think about what that would do. So I'm skipping a huge section of math right here to convince you of this. But it turns out that the correct mathematically principled way of modeling altruism in this scenario is to tell the self-driving car, if you want to be altruistic, just pretend that there's twice as much traffic as there actually is. Okay, so that's our model of altruism. Just pretend there's twice as many cars on your road than there actually are. So what would happen if the engineer came to one of these cars and programmed it to be altruistic? Well, that car, suppose we're in this scenario where there's 4 cars on the top road, that car that is now thinking altruistically, anthropomorphizing like crazy, and I apologize for this, but it's hard to get away from in this discipline. So this car is now going to imagine if you will, that there are actually 8 cars on that road. So if it's altruistic, that means it's pretending there's twice as many cars that there actually are. And if there were 8 cars on the road, the travel time would be 2 hours. And so now, excuse me, what altruism does is it says, now take this modified kind of imaginary cost that you see and pretend it's the real travel time, and then make your decision. So this car says, well, it's taking me 2 hours to drive on this upper road, and I can switch to the lower road for an hour, so I'll do it. And thereby changing one car to being altruistic, we improve society's experience. And we actually do so without hurting that car. So that's another really nice aspect of this, is that the altruistic car isn't worse off than it was before. Right? It had an hour travel time. Now it still has an hour travel time. But by leaving, it's made everybody else better off. So we can continue to do this. And it turns out that no matter how many cars you make altruistic, eventually you hit a point where you saturate and you're at the optimal point. And if you made more altruistic, you would stay optimal. Everything would stay fine. Those 2 cars that are up on the upper road would imagine that the travel time is an hour, and then they would see no reason to change from this. So it turns out that if you analyze with this particular example, this particular thought experiment, you come up with these conclusions. So the first one is that altruistic self-driving cars improve congestion, right? They make things better from a system level perspective. They do this even if only some of them are altruistic. So even if I just made one of those cars altruistic, that improves things. And it appears that they can do this without making others worse off. And so this is enough good bullet points for us to start to think, let's just make cars altruistic. Like if we ever have the opportunity to make a car altruistic, we should do it, because it seems like it makes things better without making anybody worse. So you might take this intuition, stash it away in your brain as an engineer, and then move forward. And maybe someday you find this transportation network. So this one's a little bit more complicated, not by a huge amount, but a little bit. Now we have 2 source nodes. So there's 2 places that people are starting from. There's 4 cars that begin from each of those source nodes. And now there's this extra link in the network. And this extra link, it always takes up 2 hours to traverse, is what this does. So it's a link that seems like it would be obvious never to use, right? It's always going to take 2 hours. But if everybody is selfish, if all these vehicles are selfish, or they're all only delay sensitive, they route like this, right? And nobody uses that red link, that inefficient red link. So here, now we have everybody from the lower source using that lower path, everybody from the upper source using the middle path. And we end up, if you do all the math and add it all up, you end up with a total travel time of 8 hours. So the engineer, not doing her analysis completely, comes along and says, hey, I know that adding altruism is good. So let me take this car and make this car altruistic. So what does it do when we make this car altruistic? Well, it makes this car imagine that the travel time on this road is 2 hours, right? Twice, in other words, twice what it would be if the traffic was twice what it actually is. And so if it's imagining that the travel time is 2 hours, then it looks up at that red road that only takes 2 hours minus 1 minute, right? A tiny bit less. And it says, hey, that red road is better. So I'll switch. And then what happens? Well, then, the next day, one of the cars that's down on the green road looks at the blue road and says, hey, there's essentially an open spot in the blue road. Right? The blue road only takes 45 minutes. So I'm going to switch up. And so then once we get back to an equilibrium, by changing one of the cars to be altruistic, we've caused it to deviate without make itself worse off. Right? So now it's taking 2 hours when it would have taken 1, but now nobody else's experience is improved. So the altruistic car jumped up, made itself worse off, and another self-interested car jumped in to take its place, and now nobody's improved. And our total travel time has gone up to 9 hours. And so it's not too hard to follow this through and to say, look, if we did this with all the rest of the vehicles, they each in turn would switch up. And then after it switched up, one of those cars from the green path would jump up to take its place. And we'd end up with this configuration where now the total travel time has gone from 8 hours to 12 hours. simply because the engineer took the intuition that came from the previous thought experiment and applied it here when for some reason it doesn't apply here, right? Turns out it doesn't apply here because the two cars have separate sources. If they had the same source, then everything would have been fine. But that analysis is required to be able to make the decisions to embed these things in here. So I'm essentially done, and I just want to talk about what's on this slide and then open discussion. So if we think about comparing these two machine policies, selfishness and altruism, what we see is that if you choose the selfish policy, it's not optimal in general. Like if a machine acts in a selfish way, that doesn't optimize anything in society. But it could be better than other options. So, for example, in the escalator example, the selfish policy, where the robot walks up the walking lane, could be better than the altruistic policy because it doesn't make the people behind the robot angry and then want to destroy the robot. Or, like I think it was Bruce brought up, it leaves the lane open for the stretcher, right? There could be reasons why we actually want to make this robot selfish rather than altruistic. And then in the transportation network, the selfish policy is not optimal in general, but the altruistic policy can actually lead to worse outcomes if it's not applied in a principled way. So the altruistic policy you can think of as this sort of risky policy. And so what I like to tell people is that if risk aversion comes into our optimization here, we should consider making the machines act like people and be selfish. But sometimes, if we have the right tools at our disposal, employing some kind of an altruistic policy on our socially integrated machines can lead to some improvements. But we have to understand it well. And so I'm going to leave this slide up. And I guess I do have a couple more. Yeah, that's right. So this is just a rehash of what I had earlier, where I think we need to move beyond simply thinking about technical correctness as our goal of good engineering, and move towards both technical correctness and good interactions with society. So I just wanted to leave you with a slide that says something about what I'm doing about this. So I teach a game theory course in the computer science department. I'm teaching that right now. And next week is ethics week. So we'll be talking about these exact examples with quite a bit more mathematical detail in that class. And then next year, I'm going to teach a social networks class. And so there's a huge variety of interesting ethical challenges embedded in social networks as well, which we have a little bit of time we can chat about afterwards if you want. But with both of these classes, the goal is to teach students the mathematics of interaction, to start to train people a little bit more in thinking about the full system, not just engineering by itself, but integrated with society. And then I'm seeking opportunities. The pandemic has made this challenging, but I'm seeking opportunities to deliver public lectures talking about this. And so I'm talking to the IEEE and things like that. And then I think what we need to be thinking about from a curricular standpoint is that we need to make sure that we don't ignore social science and things like decision theory and maybe economics, maybe philosophy in our engineering curriculum. There's a push in some quarters to try to make engineering and computer science education more technical and leave away all the junk from the social sciences. And I think that's the wrong direction to go. And that we need to be training people to think more about social embeddedness and not less. And then for any educator out there ever teaching anything about this, the thing that you should always teach is that you should assume that when interaction gets added to a system, or when a feedback loop gets introduced into a system, that you're going to have counterintuitive outcomes. The intuition that you build up from thinking about these one-directional interactions is rarely true once you connect everything together in a feedback loop. So with that, I want to thank everybody so much for being here and open the discussion. Let's see what kinds of discussions we can have.
Okay, I see there's quite a few questions in the chat if you are able to access it.
Yeah, let me organize my videos here on the monitor, and then I can.
Adam had a good point about function versus perceived function. Maybe Adam would like to ask that.
Oh,
And
that was just commenting back. I apologize. My mic isn't working the best.
Oh, I hear you now.
So yeah, that was just going back when you were asking for comments about the elevator dilemma.
Yeah.
And talking about do we prioritize function or perceived function? Kind of go how the social system's looking at it, and then in order to address that, how do we educate? Do we choose then to educate the social system to preserve maximized efficiency, or do we just count on those kind of social constructs we already have in place?
Yeah, I mean, great question. No, I don't think there's an easy blanket answer. I think, to your first one, the perceived, what did you say, function versus perceived function? Perception matters, and it has it's part. I mean, perception is a crucial part of this feedback loop. It's one of the key ways that the arrow goes towards the people. It's not at all clear to me whether it's better in general, or whether there's even a way of saying it's better in general, whether we should say prioritize function or perception. But they both need to be considered in the loop. And then, do we educate versus do we assume people are going to be acting in self-interest? I hope both. I think, I expect you'll never have perfect acceptance of the role of like the robot that's doing crowd control. There's and this is probably true, especially in the United States, but there's probably always going to be a subset of people who, if there's a robot doing crowd control, that robot is an agent of the deep state and should probably be pushed onto the train tracks. I don't know how to get an educational message to everybody and get everybody to buy into it. But it doesn't stop me from trying. What my research typically does is it says, let's not imagine that we can teach people to be altruistic. Like, let's accept the reality that some of them are going to be selfish and then design accordingly. But
design for incentivized systems, rather.
Exactly, right. Yep.
So the other big question I had was more about acceptance and adoption of the model that you're doing of altruism and versus selfishness.
Yeah.
And obviously, we kind of touched on that answer there. We have to somehow incentivize the development of that model. But I'm really I'm kind of focused. What you said all made sense, but how do we get the end users to buy into it? Like, you're correct in that the altruistic cars aren't having harm to themselves, but they're also not gaining the maximum benefit. They still have the hour drive versus the 45 minutes. So why should the people who are adopting the system be the ones that don't get the maximized benefit? How do we set that, or how do we get that buy-in, or is there some deception that's in there for a system that isn't universally adopting this practice?
Yeah, I think that's a fantastic question. I think that's, in terms of like this model with the transportation network, all you can do is feel sorry for whoever's riding in that altruistic car. We're really throwing them under the bus. But I don't have a great general path forward on.
So that's
how do you do adoption.
That's where my thoughts were going. Yeah. And I think we already touched on the answer. Somehow in the system design, we have to develop incentivized based nodes or strategies within the system in order for it overall to make sense. But I'm just looking at design and structure and all those things. And I definitely believe there is such a thing as benevolent deceptions, but how do we get users to buy in?
Yeah, I don't know. I think, I mean, I have a paper that's half written, and I can't bring myself to submit it yet anywhere that's about benevolent deception. And I don't like benevolent deception. I think that it served the country poorly at the beginning of the pandemic, and that's a kind of a recent example of that. I think that we should be aware of just the reality that it's going to be hard to get the perfect optimal thing to happen. And I think that's a mathematical reality that, you know, there are limitations on how well we can make these self-driving cars optimize stuff. One of those limitations is just there's people riding in them or people who own them who have to pay the gas bill. And so one of my big picture interests from a research perspective is understanding those fundamental limitations. But yeah, I think those are important.
Yeah, a couple things. I agree with you on the benevolent deception. It seems like there are more morally positive ways of doing that. I mean, the airlines has this idea of we'll give you some benefit, or for not taking this flight, you know, because we're full somehow. And so some people don't mind reading their novel and getting some benefit either now or later. And then, you know, to be dishonest, then people don't trust the system, right? And they can begin to make conspiracy theories about how they're being mistreated. And I think we have a lot of history of that being generally not good.
Right.
You know, they're willing to make a sacrifice once in a while for the whole. So a lot of people are, if they trust it. If they trust that it's going to, you know, what goes around comes around.
Right.
And another concern I have is with, you know, and it's not so much one time or a little, you know, a few occasions in life, but at least if you follow Aristotle, in my experience is long term, that he has a lot of good to say, that happiness itself, or thriving as he, you know, thriving as he talks about it, is a matter of moral growth and prudence and all those things, that to become a free and happy human being is to have decisions and difficulties, and to find the best we can the truth, or what the knowledge that we need, and then take an increasingly noble action. And if we design systems that don't let people make those choices and then learn, well, that wasn't so good, or that wasn't so good for somebody else.
Yeah.
Then what happens to humanity with this? So, you know, there's even a broader interaction and feedback that's longer term and more global, and it's very difficult to model. And then, you know, the last thing is, maybe, you know, this morning my objective function is different than typical. I don't really want to get there by the fastest route. I'd like to see the buildings in Glendale. I want to see more trees today. You know, I just kind of, I mean, we all experience that, right? I drive through Pueblo, different routes, and just for variety. And
sure.
And so how do you know, it's very difficult to model that.
Sure. Yeah. Right.
But it's important.
Yeah, the hope is always that those things, you know, which are sort of random and stochastic and hard to model, that those, you know, average out. But that's painting with these massive broad strokes and maybe doing violence to the reality. I'm really interested in what you were talking about this long-term feedback loop, where basically you're asking, you know, can we be constructing ourselves a moral crutch and causing ourselves great harm? I think, you know, that sounds completely plausible to me, that that making decisions now, I mean, the game theorist in me says we're playing a game with, in some ways, our future selves, and that need not lead to something good, even if it feels like we're making a good step right now. So very interesting.
Yeah,
very interesting idea.
Very good cases here. Yeah, for discussion. Thank you.
Yeah.
Hey, we are just about out of time. did ask Philip if you could just finish up maybe about how the Daniels Fund Ethics Initiative principles apply. I mean, we talked a little bit about honesty and integrity, but what about transparency? I mean,
Right.
everyone thinks that this car is going to get them on the fastest route, but it might not happen.
Yeah, right. So that's a great, the transparency one's a great example. It's not clear that the altruistic policy is transparent to the occupant of the altruistic car, or maybe maybe making it transparent runs you up against these incentive constraints. So making it transparent would mean the occupant has a switch that they can flip that says, I want to be altruistic today. And you tell them how much time they're going to lose by being altruistic. I think fairness is a hugely challenging question in these areas. So fairness is the next one down on the list from transparency. How do we ensure fairness in these things? Is the robot who's standing on the escalator being fair by making the people who are waiting in line back way down at the bottom of the escalator, making them get where they're going faster? Or is it being fair by walking and letting the people behind it get there faster? I think respect is an interesting one as well, where again with the robot on the escalator, if it is standing in the walking lane, that feels disrespectful to the people behind it. Rule of law is a really tricky one because we're in this phase where the self-driving cars are a great example, where the law is not clear how a self-driving car should behave. So I think we need people in the legal community to be on top of this and aware of kind of staying in front of the challenges with this. And then viability is a big piece of what I think about. How do these kinds of systems both promote good in society and stay and remain accepted by society? Like, how can you make them viable socially? We live in this world that's kind of torn between voting with dollars and voting with votes, and both of those things can cause the downfall of a poorly thought out system. So how can we promote the viability of systems that we can design which do improve conditions for people?
Well, thank you, Philip. It looks like we're out of time, and I know that a lot of people enjoyed your presentation, and so thank you very, very much. And I'm sure that you've gotten everyone thinking about all of these things, and might think whether or not to get one of those self-driving cars or not.
Well, thanks everybody for being here. It's been a pleasure. I've really enjoyed the discussions.